Hello, my name is Wyatt Rabita, and this is my Physics 2212 Lab 4 presentation on magnet. Introduction. The purpose of this lab is to measure the effect of the magnetic fields of a bar magnet at different distances and compare the real-world analysis with the computational model. The materials we used were 2 meter sticks, a magnetometer mobile app, a small bar magnet, WebVPython for model purposes, and Microsoft Excel. Here are some brief results of the experiment. The value for mu was 111, the value for n was negative 2.1173, and the value of k was 2.22 times 10 to the negative sixth. Here are some fundamental physics principles that we'll need to have for this lab. First up is the Biot-Savart law. This expresses the magnetic field at an observation location based on particle speed and charge. The magnetic dipole formula, which expresses the magnetic field of a dipole based on the magnetic dipole moment, symbolized by mu. And the relation of B to R, which expresses the magnetic field B in relation to the distance R in a sloped line formula, where ln of B equals n times ln of R plus ln of K. Initial conditions of the lab. The system is the magnet and phone, and the surroundings are everything else. The magnetometer was oriented to Earth's magnetic north-south axis, where B of the Earth in the x direction is equal to 0. The meter stick was placed perpendicular to the phone. Finding the magnetometer. Using the meter stick and the magnetometer app, we found where the magnetometer was inside the phone, allowing us to accurately measure distances off and on axis. Measuring distance with Bx. Now knowing the location of the magnetometer, we can measure the distance at which Bx attains a certain value. This allows us to plot R and Bx against each other to find a common relation. Plot of ln Bx versus ln R. This is the plot of ln Bx in relation to ln of R. The formula of the line y equals mx plus b can be rewritten to the relation formula in the fundamental physics principles slide, where y is equal to ln Bx, b is equal to ln of k, and x is equal to ln of R. And we get ln Bx is equal to n times ln of R plus ln of k. Finding mu from relation. Using the fact that b both equals k r to the n and km times 2 mu over r3, we can set up an equilibrium equation to solve for mu. Doing all the math and plugging in 2.22 times 10 to the negative sixth for k, 1 in for r, and negative 2.1173 for n, we find that mu is approximately 111 a times m squared. Off-axis B-net measurement. A distance d perp was measured when the magnitude of the net magnetic field was 100 microteslas. Each value of the net magnetic field was calculated at distance d from the magnet, giving the final column B-net of t. Computational model. Using GlowScript, I created a computational model to show the magnetic field of a bar magnet on and off axis. The screenshot of the left code creates a magnet and assigns a mu value, but also defines the dipole B function, which will be used to calculate B. The right screenshot of code calculates and displays the B arrows at each on-axis and off-axis location. Comparing results. The code up at the top defines the location and the magnitude of the 45-degree B arrow. This model displays the arrows for the magnetic field of the magnet and their relative sizes. Comparing the model to the real-world measurement, the model is off by a factor of 10. Potential sources for error. Number 1, the lab area was filled with other electronics, things that could affect the calibration and measuring using the magnetometer. 2, the exact position of the magnetometer was not found. Number 3, the magnetometer app was very finicky and had to be restarted often. The measurements were not accurate. Extra questions. What if you hadn't oriented your experiment to compensate for magnetic north, and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? Well, since B Earth at the x component does not equal 0, it will have an impact on the measurement of the magnetic field of the magnet at further distances. The measured distance at which a certain magnitude of magnetic field is obtained will be greater or smaller in relation to the angle you rotate the meter stick. What if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? By sticking two magnets together in series, the magnetic field they produce becomes stronger in magnitude, but does not change directionally. That's it for my Physics 22-12 Lab 4. Thank you for your time.